Yes. Next, we will see the Fermi-Dirac distribution law. We know that Fermi-Dirac statistics is applicable to the particles which are identical and indistinguishable. Yes. So what happens here? The wave functions of the particles overlaps, and the particles will be identical, and you will not be able to distinguish the particles. And again, these particles will have the half integral spin. Yes, half odd integral spins means the spins will be either 1 by 2, 3 by 2, and so on. And we know these particles are known as Fermi ions. Yes, and these particles, we have to remember, these particles will obey the Pauli's exclusion principle. Means if you have a given energy state, in the energy state you cannot have more than one particle. Yes, either the particle will be uh, either you have zero particles in the state, or the particles will be at most one in a given energy state. So the examples of such particles are electrons, protons, neutrons, etc. This all obey the Fermi-Dirac distribution law or Fermi-Dirac statistics. Then uh, the next thing is you have to derive or write the Fermi-Dirac distribution law. So here, if you are able to remember the previous Bose-Einstein distribution law, then you can easily write this Fermi-Dirac distribution law also. Why? Because there you have a minus 1, here you have a plus 1 in the denominator. Yes. So the Fermi-Dirac distribution function states that the probability of a Fermi ion occupying a state of energy E is given by f of E is equal to 1 by exponential power alpha plus E by kT plus 1. Again, the same thing, the alpha is a constant, and we know alpha is depends upon the properties of the material or Fermi ions, and it's also a function of temperature. And as usual, K is your Boltzmann constant, and T is the absolute temperature. So this is your Fermi-Dirac distribution law. You have to put this uh, law into our familiar equation, normal distribution equation, that is Ni is equal to, or N of E is equal to G of E into F of E. So here what we do is we will be dealing with electron gas here. Why? Because we know electron is a Fermi ion. So if you take a conductor of volume V having n free electrons, then the total energy of the electrons is taken as E. So this energy E is distributed among all the n electrons. So according to your Fermi-Dirac distribution law, the actual number Ni of the electrons with energy E is given by Ni is equal to GIE into F of E, is nothing but GI by again E to power alpha plus E by kT plus 1. So we have to remember that GI is nothing but the statistical weight. So it gives the number of phase space cells with energy E, means nothing but the total number of states available for the particles to be occupied. Yeah. Uh, why? Because when you need to arrange the particles, you should have some space for the particles or the cells for the particles. So GI is nothing but it is the available cells for the particles to be occupied. Yes. So this equation is nothing but your Fermi-Dirac distribution law. Again, if you assume that the energy is continuous and the range is very small, means the success energy between the successive electrons is very small, then you can put dE there. That is, we have to assume that the continuous energy distribution of among the electrons uh, means the energy distribution is continuous among the electrons. Then the number of electrons within the energy interval E and E plus dE is given by N of E is equal to your G of E dE by again the same thing exponential alpha plus E by kT plus 1, where G of E dE is the number of phase cells within the energy interval E and E plus D. Yes. So that is the statistical weight. Now you got the equation. The next job is to apply this equation to electron gas. It is the application of your one of the application of your Fermi-Dirac statistics. Yes. Now you will be confused. What is an electron gas? Okay, we have a number of gases you have known, but this electron gas is not a a special type of gas. It's nothing but we know in the metals are very good conductors. So why they have the good conductivity? Why? Because they have a large number of free electrons. Yes, so these free electrons will be moving inside the conductor, and they will be colliding with the fixed atom. Why? Because we know this lattice. In the lattice, the atoms will be fixed, but within the atoms, the electrons will be moving freely. So this electrons will behave as a electron gas. So this therefore the electrons will be moving freely inside the metals, and they are known as electron gas. So we know electrons will have half integrals angular momentum in the unit of h by 2 pi. They are called Fermi particles or fermions, and they obey Fermi Dirac statistics. Yes. So here again, you should be very particular about the Pauli's exclusion principle. Why? Because when you distribute the electrons in the different cells, uh, the occupancy should be either 0 or 1. So we'll see the Fermi energy of electron gas. First, you should know what is Fermi energy. Yes, this is a very important term, Fermi energy, and again, it's very simple also. So, in case of particles obeying Fermi-Dirac statistics in thermal equilibrium at absolute zero, the energy levels from 0 to a certain value of EF are occupied by the particles. Means you can imagine 1, 2, 3, 4. Like this, you have a number of energy levels right from the ground state, means 0 to uh, uh, a higher number. But what happens? All the levels will not be occupied, only the levels up to some energy EF are occupied. So all the energy levels above EF are vacant. Yes. So it means that EF is nothing but it is the energy of the highest occupied level at absolute temperature equal to 0. So such energy level is known as Fermi energy level, and the energy of that Fermi level is nothing but Fermi energy. Yes, so we need to remember that at absolute 0, all the energy levels from 0 to a particular level EF are filled, and all the energy levels above EF are empty. This energy of the highest occupied level is known as Fermi energy, and that level is known as Fermi level. So we know the Fermi-Dirac distribution law. Already we have derived this. So according to the Fermi-Dirac distribution law, the number of particles having their energy lying between E and E plus D is given by your n of E. dE is nothing but G of E dE by again E to power of alpha plus beta EI plus 1. Don't be confused with beta. Beta is nothing but 1 by kT. So now what we are doing, we are applying this Fermi-Dirac distribution law to uh, electron gas. So again the same problem. You should know the number of available energy levels. That is what is the statistical weight here. As I told in the previous topic also, when you are taking the Maxwell-Boltzmann distribution, you take a spherical shell of radius p and p plus dp, and means within the thickness dp you are calculating the number of gas molecules. Then if you are going to your Bose-Einstein distribution, there in the case of photon gas, again what we do, we will take the number of photons which are lying between some momentum between p and p plus dp. Here so what happens, if you take a system of free electrons enclosed in a volume V, then we have G of E d is nothing but 2 into 4 pi p square dp into V by h cube. So here we have a factor 2. Why? Because these electrons are obeying the Pauli's exclusion principle. So if two electrons with spin up means plus 1 by 2 and down spin minus 1 by 2 can be accommodated in the energy state. Yes, you can have the electrons with spin up and down which are accommodated in a energy state, and V by h cube refers to the translational energy state per unit volume in fixed space. So this factor you have to remember. Now if you substitute this statistical weight or the factor or the number of electrons which are occupying the states in your distribution law, you will get a equation something like this. And now this is nothing but number of particles which are lying in some energy ranges. So if you want the total number of electrons in the system, you have to definitely integrate this from 0 to infinity. So when you are applying the limits, we have to remember the Fermi gas or Fermi level. So we know at absolute zero, for all the energies less than the Fermi level are occupied. Means your distribution function f of e is taken as 1, and we know that you will not be having any electrons in the energy levels above the Fermi level. So if the energy is greater than Fermi level, EF or Fermi energy, then you won't have any particle there. So f of e is 0. So using this, you can integrate, you can put the limits from e is equal to 0 to EF, and you have to take f of e equal to 1 for that. So this will be simplified, and again we have to convert this, means you have dp here. So in place of p, we have p square is equal to me, where m is the mass of the electron, and when we know energy is 0, p will be naturally 0, and when energy is equal to Fermi energy ef, in p also you will be getting ef. So you will be writing n, you will be getting n. From there, if you do simplifications, so you will be getting your Fermi energy F to go to power of 3 by 2 is nothing but equal to 3h cube n by 8 pi 2m to power 3 by 2. We know n is nothing but density of electrons in the assembly, that is capital N by B. From that means you can, uh, wherever you have n by B, you will be putting a small n. Then you will be getting Fermi energy EF is nothing but h square by 2m, 3n by 8 by whole to power of 2 by 3. So this is the equation for the Fermi energy of the electrons. So we can say that your Fermi Dirac statistics is very successful in finding the Fermi energy of the electron gas.